Welcome to Maths with EJD. In this video, I'll be talking about physics applications of binomial series. Physics applications of binomial series. Now, in the previous video, we had talked about using binomial series for algebraic, uh, for simplifying algebraic expressions, and we see how useful that was. That sometimes maybe an expression has infinite terms, or it has that's six terms, and maybe you just need the first two terms, or you want to jump to a particular term in the process. You can actually always do that. All right. So here, we want to see how we can use binomial series in physics like that. So we see here that binomial series, the binomial series is vital in approximating. Okay. Once things are getting modeled up like that, it's just better to give it space. It is very vital in approximating expressions in physics, particularly, particularly for small values of variables. Okay, so, and the first thing we'll be looking at here is the idea of small angle approximations, small angle approximations. So for small angle approximations, right? Imagine for small angles theta, for small angles theta, trigonometric functions, trigonometric functions can be approximated using the binomial expansion, using the binomial expansion. Okay. Now imagine this particular one now that you have okay, I think we should make it like an example. Okay, I mean, for small angles theta, trigonometric functions can be approximated using the binomial expansion. Now, what I'm going to do that there is this, imagine that you see that cos theta is approximately 1 minus theta squared over 2. And that is where sine theta itself is approximately theta. In that case, when the angles are very tiny, you know, when theta is very small, sine theta is almost theta itself, and cos theta is like 1 minus theta squared over 2. Now, let's take an example to drive that point way all the way home. Now, imagine this example. Imagine this example. You need to approximate square root of 1 minus theta squared for theta equals 0.1. 0.1 is such a tiny value. So imagine this now. We have square root of 1 minus theta squared. Normally, that is like 1 minus theta squared. I mean, 1 minus theta squared raised to power half. That's what that is. So it means we need to use that idea of for fractional powers now. So I will just go straight and do that. We know what we should do already, right? We have so here we take the first expression, the first number, we raise it to power half, and we take the second one, theta squared, we raise it to power zero. So the half and zero, so half plus zero is always half. We divide that by we divide that by 0 factorial generally, right? Then the next thing we have now is to bring down power half. The power comes down. So when we bring down power half now, then we now have um 1 raised to power half minus 1, that's minus half, okay, into minus theta squared, uh, that's minus theta squared raised to power 1, because minus half plus 1 must always give us half. So this divided by 1 factorial. Now, well, we might want to even take it further, and we have half into minus half into 1 raised to power minus half minus 1, that's minus 3 over 2. And then we have minus theta squared raised to power 2 divided by 2 factorial. Okay, we have all this. Of course, this is an approximation, since we can have infinite terms of this. So now, this is approximately 1 raised to power half is 1, minus theta squared raised to power 0 is 1, 0 factorial is also 1. Then plus, we have half of the 1 raised to power half is also 1. So this is 1, this is 1. So that's z minus theta squared. We have that minus theta squared down there. And this is 1 factorial. Then for this time, we have half into minus half. 1 raised to power, this is also 1. Then minus theta squared, that's simply theta raised to power 4 divided by 2 factorial. 2 factorial is just 2. So, that's the approximation we have right there. Then we go on and tidy things up a little bit more. So 1 times 1 over 1 is simply 1. Then here, you have minus, so that's minus. Okay, well, because of this now, I want to still do something. So this is like half into 1 into minus theta. What happened there? So this should be, okay, I think I should write this differently. So this is minus theta squared. That is minus theta squared raised to power 1. Yeah. So that works. So here we have minus theta squared raised to power 1, which remains the same, right? Then plus, now this 2 under, now we can bring it up as half. Then this half that was there before is still there. Then we now have that minus half. Then 1 is there, theta raised to power 4, and all of that will go. So here, this is approximately now, so this is approximately 1 minus, oh, sorry, this actually plus, right? Okay, so now this is approximately 1. All right, this is 1. So because plus and minus, that's minus half theta squared, then plus, okay, still, that's still minus, right? So because plus and minus is still minus, so it's minus 1 over 8 theta raised to power 4 plus all that. Now, the interesting thing here is that, we're approximating for 0.1. Now, usually the approximation would be, okay, we can just say since theta is very small, of course, or I can say since theta equals 0.1 is considered small, then we can have this approximation that square root of 1 minus theta squared is actually 1 minus half theta squared. Because, I mean, going all this way now, it's more like theta raised to power 4, that you're going to have so many zeros already. So if we now use what we've been given, that theta is 0.1 now, so we can just say that square root, so therefore 1 minus 0.1 squared will simply be 1 minus half into 0.1 squared. Okay, so which is, of course, this is approximation, so approximately 1 minus half into 0.1 squared, that's 0.01, and that is approximately 1 minus 0.01, that's 0.005, and that is approximately 0.995. Okay, so that works in that situation. All right, so that's one example right there. That's an example talking about small angle approximations. We can also have example in fluid mechanics, which I'm not going to dwell too much on. So, of course, fluid is something we also talk about in physics. it also goes into engineering somewhat. So if we talk about fluid mechanics in this situation, we know that in models, in fluid flow models, binomial expansions, binomial expansions linearize. They actually linearize non-linear terms. So if you want to linearize non-linear terms, that can help. Okay. Imagine, for instance, for instance, 1 plus x raised to power n is approximately 1 plus nx. Okay. We know how that works now because even if we use the general formula, so you have 1 raised to power n, x raised to power 0 over 1, that's all one like that. Then next you have n times 1 raised to power n minus 1, x raised to power 1, So that's just easy approximation. You have 1 plus nx like that. So, and this is actually this is used to simplify, this is used to simplify velocity, is used to simplify velocity or pressure field equations or pressure field. It is used to simplify velocity or pressure field equations. Okay, so we have that. Right, so that brings us to the end of this particular video. So if you have not subscribed to this channel, you have more coming. In the next video, we're talking about applications in finance and engineering, like that. So if you have not subscribed, you want to do that right away and hit the notification bell so you can always get alerted each time a new video is released. Comment, let me know how helpful these videos are for you. And also, let me know if you have a problem for me to solve or a topic to treat. Find time to do that. Then like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye.